Have Ketan Bundle who will tell us about the Advanced System GCD program.
So, thank you very much, and I would like to thank the organizing committee for inviting me to this workshop.
Ketan, is the thing turned on? Mic turned on?
Hello?
Yeah. Okay.
Yeah? Okay. Fine. So, this talk will be on the recent developments and concrete open problems in the GCT program, where GCT stands for Geometric Complexity Theory. So the main reference for this talk will be this article, Geometric Complexity Theory 5, Efficient Algorithms for Noether Normalization, or GCT5 in short. The extended abstract of this article appeared in Fox 2012, and the journal version appeared in JMS 2017. This article is very crucial for the GCT program because certain basic connection between invariant theory and complexity theory, which was discovered in this article, lies at the basis of this program. And also this article lays down a substantial part of this program and also the skeleton of this program. Well, Avi has made my task easier because he has already introduced everybody here to basic notions of invariant theory, and I'm going to assume that everybody knows what orbit closures means, rings of invariance, and so forth. Okay, so I'm just going to assume familiarity with this. Now, I had given an overview talk on this article. There was a semester in Simons Institute few years ago with focus on GCT, and there was a special workshop on GCT. So in that workshop, I had given an overview talk on this article. Since then, several fundamental developments have occurred in the context of certain conjectures and open problems which were posed in this article. So what I want to do today is give an updated overview, taking into account the developments which have happened since then. And also I will pose some open problems which assume significance in view of this development. So that is the goal for this talk. So with that, let me begin by stating a certain basic problem in GCT called the VP versus VP bar problem. And for that, let me begin by recalling a fundamental conjecture due to Valiant, which says that VP is not equal to VNP. Now, I'm going to assume that everybody here is familiar with basic notions and definitions of algebraic complexity theory, and so everybody knows what is VP, what is VNP, and so forth. Now, the basic hardness of hypothesis of GCT, which was introduced in the first article, GCT1, joint with Milind Soni. This is a certain straining of Valiant's conjecture, which says that VNP is not contained in VP bar, where VP bar is a closure of VP, and VP bar is defined from VP by just replacing the notion of exact computation in the definition of VP by the notion of infinitesimally close approximation. And this notion of infinitesimally close approximation is basically similar to the one that is used in the definition of border rank in the literature on matrix multiplication. So everybody should be familiar with that. So you make that change. So the relationship between VP and VP bar is something similar to the relationship between rank and border rank in matrix multiplication. And anyway, I would give a precise formulation, restatement of this in the language of algebraic geometry later. Now, this hypothesis is important. This training is important because any realistic approach to the VP versus VNP problem can be expected to prove this training of Valiant's conjecture. Because, for example, the current based lower bound for the permanent, quadratic lower bound for the permanent due to Mignon and Rosser also holds for infinitesimally close approximation. And similarly, all known lower bounds for the permanent in restricted algebraic models of computation also hold for infinitesimally close approximation. And so we expect that the same phenomenon would continue in the unrestricted world also. And so any realistic approach to the VP versus VNP problem can be expected to prove this straining of Valiant's conjecture. Now, a basic question which arises in the context of these two conjectures is, are they equivalent? Okay, and or this is the same thing as asking, is VP bar equal to VP? And this problem was studied in GCT1 and subsequently also by Burgeser and others. Now, at the surface, it may seem that this probably shouldn't be such a significant problem, because VP bar at the surface may appear like just a slight strengthening of VP, okay, and so forth. So it may appear that this is not such a serious problem, and why should it be so important in the context of the VP versus VNP problem? If it appears to be that way, it is an illusion, because it turns out that this problem is actually related to very deep fundamental issues in algebraic geometry and representation theory, which I'm not going to go into in this talk, but I will at least elaborate on this a bit more later. So it is actually a very deep question, a deep and fundamental question related to foundational issues in algebraic geometry and representation theory. And at present, there is no concrete evidence either way, whether VP is equal to VP bar or not. And so we are going to take a neutral perspective and be completely open and consider both the possibilities, equality as well as inequality. Now, this problem is a basic discovery of the GCT program, because you see, before GCT, it was never realized that this is such a serious and deep issue. Because before GCT, the study of VP versus VNP focused on VP, okay? And though the notion of infinitesimally close approximation was studied in the context of border rank in matrix multiplication, there is no such thing as VP versus VP bar problem in matrix multiplication. So this is where the GCT begins. Okay, so the discovery of this problem is a basic discovery for GCT and also for theory of computation. Now, the next thing one may ask is, what is so important about this problem in the context of VP versus VNP problem? Because after all, you just want to separate VNP from VP. Why should it matter whether it is even equal to VP bar or not? And so another basic discovery of GCT in GCT5 is that VP versus VNP problem is hard because this problem is hard, and this is far from obvious. And so the next question is, in what sense? Okay, and that we are going to explain that in this lecture. Okay, so for that, let me begin by reformulating the VP bar versus VNP problem in the language of algebraic geometry. And instead of reformulating the VP bar versus VNP problem, I am going to reformulate the VP WS bar versus VNP, where WS stands for weakly skew. So VP WS is the same thing as VP, but using weakly skew algebraic circuits instead of algebraic circuits, and weakly skew algebraic circuits correspond to symbolic determinants. Okay, so VP WS is like VP but using symbolic determinants in place of circuits, and VP bar is just then again taken as the bar of closure operation, just like the VP bar, analog of that. So I'm just going to do this for the sake of simplicity. And so for reformulation, let me just introduce some basic terminology. Let Y be an m by m variable matrix, X an n by n submatrix of Y with n less than m, and let Z be any entry of Y outside X. Okay. Let V be the space of homogeneous forms of degree m in the entries of Y, and let P of V be the projective space associated with V, and let sigma of det m inside projective space V be the set of all points in this projective space which correspond to non-zero homogeneous polynomials in the entries of Y, which can be expressed as determinants of symbolic m by m matrices whose entries are homogeneous linear functions of the entries of Y. Okay, so this is what sigma of det m inside this projective space P of V is, and it can be shown in the language of algebraic geometry that this is a so-called constructible set, which means it is obtained by some number of algebraic varieties using the operations such as and, or, and complement. Okay. Now, it is known in algebraic geometry that such constructible sets are very unwieldy from the mathematical point of view. So instead of dealing with a constructible set, one usually deals with its closure, which is then a variety. So that is what we will do. So instead of dealing with sigma of determinant m, we will take its Zariski closure, and which we will denote by delta of det m inside this projective space PV. This is the Zariski closure of sigma determinant M in projective space PV. This then is a variety, and this is what we'll deal with. Okay. Now, this delta of determinant M also equals the GLM orbit closure, and Avi has already described what an orbit closure means. So it also equals the GLM orbit closure of the determinant function in that projective space PV under the natural action of GLM square C on the projective space V. But actually I am not going to make use of this orbit closure structure of this set in this talk. It plays very important role in GCT, but in this talk I am not going to make use of it. But since this set is referred to as the GLM's orbit closure of the determinant, I will just refer to it as the orbit closure of the determinant. But though I am not going to make use of the orbit closure structure in this talk, though in GCT this is of fundamental importance. Okay, so this is the basic terminology. So with that terminology, now VNP not contained in VPWS conjecture in Valiant can be shown to be equivalent to saying that Z to the M minus N times permanent X is not contained in sigma of determinant M. Whereas the VNP not contained in VPWS conjecture in GCT1 can be shown to be equivalent to saying that Z to the M minus N times permanent X is not contained in delta of determinant M. So this is a pictorial depiction of this thing. As you can see, my drawing is not very advanced, so you have to take my pictures with a pinch of salt. So sigma of determinant M is higher dimensional, but I am pictorially showing it as one dimensional. This is a constructible set. So what is a constructible set? So you start with a variety and then take away the lower dimensional recursively defined constructible set, which is what I pictorially define showing as a whole. So these are the wholes are either lower dimensional subvarieties or more generally a lower dimensional constructible set defined recursively. And delta of determinant M is a variety which is obtained from sigma of determinant M by filling in these holes. That is what the Zariski closure operation corresponds to. Okay. So this is the now you see that the geometry of sigma of determinant M is controlled by the singularities of delta of determinant M. For example, if you take this curve and remove this singularity and you want to understand how the curve without the hole looks like, well, the shape is completely determined by actually how the whole curve looks like in the vicinity of the singularity. So even though the singularities are not part of the sigma of determinant M, those singularities are what determine the shape of sigma of determinant M. So because of that, the structure of the singularities is fundamental importance in the context of the VPWS versus VPWS bar problem, because VPWS corresponds to sigma of determinant M, whereas VPWS bar corresponds to this variety, and this whole singularities is what is going to control the shape, and that is why these are of fundamental importance in the context of the VPWS versus VPWS bar problem. Now if it were the case that all these singularities were nice from the algebraic geometric point of view, for example, if they were normal and had codimension 2 and so forth, we would have been much further off towards the resolution of the VP versus VNP problem from where we are today. Okay.
But you want to be M to be polynomially bounded in N for the statement of this?
No. Oh yeah. Of course. Yes. Sorry. Yeah. Okay. And so, if the singularities were nice, then our job would have been much easier. But unfortunately, it turns out that the singularities of delta of determinant M are not even normal. This is a fundamental result of Shravan Kumar, which was proved in the context of the GCT program. I won't go into what that means. Normal singularity means in algebraic geometry they are well behaved, and non-normal means they are badly behaved, which means this is a bad news for the VP versus VP bar problem and bad news for the VP versus VNP problem also. Okay, so this is the beginning of difficulties in the context of the VP versus VP bar WS bar problem, which is finally going to reflect into difficulties in the context of the VPWS bar versus VNP as well as VPWS versus VNP problem.
So, do you have a concrete example of something that you can write down in VP bar that I can see that it's difficult to?
Excuse me?
Do you have a concrete example of something that we can write down in the VP bar class that I can see why it's hard to be done in VP? Or
Why it is what?
So give us a concrete example of a problem which is in VP bar.
Okay, I'm not going into that because that is really related to these deep issues in algebraic geometry, which I'm not going in this thing. Yes, there are, but okay. So, what kind of difficulties? Now, to get a hold of these difficulties, I'm going to recall something called a basic result in algebraic geometry called Noether's normalization lemma due to Hilbert, which we shall by short form denoted by NNL. And this result holds for arbitrary algebraic varieties, but I'm going to specialize it to the orbit closure of the determinant because that is all we are worried about in the context of VP versus VNP problem. And after that specialization, what this result says is that there exists a homogeneous linear map psi from V to C to the K for any K bigger than dimension of the orbit closure of the determinant, such that psi does not vanish on any non-zero point in the affine cone delta hat of determinant M inside V of this orbit closure of the determinant. And what do I mean by the affine cone? It means this affine cone consists of all lines in V through the origin which correspond to the points of this orbit closure of the determinant which is sitting inside projective space V. Okay, so this is basically what Hilbert's Noether's normalization lemma says. And
it's
this
a dimension reduction.
Huh?
It's a dimension reduction lemma,
yeah.
which is very natural for this audience.
Yeah. Yeah, but he did it much before we.
No, I just want to interpret it. You write it formally, but it's a dimension reduction.
Yeah.
You can always reduce to a dimension that's just slightly bigger than the dimension of your.
Now, the important thing is that this implies that the rational map hat psi from the projective space associated V to the projective space associated with C to the K corresponding to this linear map is regular. That is well defined on the orbit closure of the determinant, means it doesn't have poles. And we call such a homogeneous linear map psi from V to C to the K a normalizing map for delta of determinant M. Okay? And with that, now we'll introduce this problem called NNL, where NNL stands for Noether's normalization lemma, which is that given delta of determinant of M, okay, with a succinct specification, construct a normalizing map psi from V to C to the K with K equal to polynomial in M. We don't require K to be as small as possible. Like here, K can be just 1 plus dimension of the orbit closure of the determinant. But we have to allow some slack and allow it to be polynomial in M. This is important. With a succinct specification, I will specify in a moment what a succinct specification means. So succinct means it should be of size polynomial in M. So let me remark here that the usual specifications of this orbit closure of the determinant inside projective space PV by its equations, or the usual specification of this linear map psi by its matrix, these are not succinct because the dimension of V is 2 to the polynomial in M, because V is the space of homogeneous forms of degree n square of M in M square variables. So the number of equations, number of variables in these equations itself is exponential in M. And similarly, the dimension of this matrix again would be exponential in M. So these usual representations are not succinct, but it turns out that delta of determinant M can instead be the coordinate ring of delta of determinant of M has a set of generators which can be encoded succinctly by an algebraic circuit of polynomial poly-M size, which also can be computed in polynomial in M time, and all this finally comes down to the fact that the determinant function has a small circuit which can be computed in polynomial size. Okay, so I don't want to get into the technicalities, but this has a succinct specification because determinant can be computed fast by a small circuit. And similarly, it can be shown that there exists normalizing map with a succinct specification, and this would correspond to, in the language that is familiar to us, the certain succinct hitting sets for VPWS bar. So in polynomial identity testing, there is a notion of a succinct hitting set for VPWS. And it turns out that this notion can be naturally generalized to the notion of a succinct hitting set for VPWS bar. And these such normalizing maps with succinct specifications would basically correspond to succinct heating sets for VPWS bar. Okay, and again I don't want to go into the details. So this is basically what succinct means at the high level. And then the problem NNL is, given delta of determinant M with a succinct specification, construct a normalizing map psi from V to C to the K with K equal to polynomial in M with a succinct specification. Okay, so it's clear what this problem is. Yeah.
So in this you don't ask for an algorithm or?
No, just this is just a problem. Just construct.
Just care about the size of the.
Huh? This is just about the size, that it has to be finally the normalizing map has to be succinct, that's all. But now the question is, what is the current complexity status of this problem NNL? Okay, that is related to what you are talking about. So before I get into that, let me remark that the problem NNL for delta of determinant M is equivalent to the problem of constructing a heating set for VPWS bar. So in polynomial identity testing, we have the notion of a heating set for VPWS. Now that notion of a heating set for VPWS can be naturally generalized to the notion of a heating set for VPWS bar. And this problem NNL is equivalent to that problem of constructing a heating set for VPWS bar. Now this equivalence in conjunction with Grobner basis theory implies that NNL is in X space. Okay. Now a recent development, a fundamental development due to Forbes and Spilka and Guo, Saxena and Sinababu shows that NNL is in P space. And there are going to be 2 lectures in this workshop later. I think one by Michael and the other one is by Nitin, where they are going to describe this result, maybe in the language of heating sets, but it's the same. And so I won't go into that any further, but let me say that it's a fundamental result for GCT because it brings down the problem NNL from X space to P space, which is a substantial drop in the complexity. But this is how far we can hope to go without knowing the relationship between VPWS bar and VPWS, because the proofs of both these results actually don't use anything more than the definition of VPWS bar. It is basically looking at VPWS bar as a black box, doesn't look inside it, basically it doesn't look inside the relationship between VPWS bar and VPWS. Now that is a good thing from one point of view, that you don't have to look inside, so that is a pro. But then that is also cons from the bad thing from the other side point of view, because without looking inside, we are not going to go much further. Okay, so to go much further, we will somehow need to know the relationship between VPWS bar and VPWS. Now, if we know that VPWS bar is equal to VPWS, then it can be shown that NNL is in pH, assuming generalized Riemann hypothesis, because if VPWS bar equal to VPWS, then the heating set construction problem for VPWS bar is the same thing as heating set construction problem for VPWS, which then can be solved in pH using the pH algorithm for Hilbert's, Nullstiel and Sart's of Koiran. Okay, and so assuming generalized Riemann hypothesis. So if VPWS bar is equal to VPWS, then NNL is in pH, assuming the generalized Riemann hypothesis.
This is still open for prime characteristic.
Yes. I'm assuming, if I didn't say it, the field is C, okay? So, or characteristic 0, okay? Yeah. Okay, so, but of course this is a big if, because we don't know if VPWS bar is equal to VPWS. So, the question is, where is NNL, okay? And so the next result in GCT5, the equivalence result, sheds light on this. It establishes basic equivalence between NNL and a variant of the hardness hypothesis of GCT. It shows that NNL is in P, ignoring a quasi-prefix, if and only if certain variant of the hardness hypothesis of GCT, that VNP is not contained in VP bar, holds. So let me first explain what that variant is. That variant basically is that some exponential time computable multilinear polynomial cannot be approximated infinitesimally closely by sub-exponential size algebraic circuits. Okay, this is basically the algebraic version of the X not contained in P/poly conjecture. Okay, so that is the variant. Let me also say a few words about the proof. So the proof is based on classical algebraic geometry, basically Noether's normalization lemma of Hilbert and the related results, and some fundamental results in algebraic complexity theory. Basically the fundamental multivariate polynomial factorization result of Kaltofen and Traeger, which is the crux of this proof, and also the fundamental results due to Heinz and Schnorr, Cabanets and Impagliazzo, and Nissen and Wigderson. I won't go into the proof, basically you just put these things together. And I should say that analogous result also holds in general for any explicit variety in place of the orbit closure of the determinant. So what do I mean by explicit variety? By that I mean any variety whose coordinate ring has a set of generators that can be encoded succinctly and uniformly by algebraic circuits of size polynomial in the dimension of the variety. Okay. Now it turns out that orbit closure of the determinant is a prime example of such a variety. Okay, and it's a basic prototype. But there are other explicit in algebraic geometry and representation theory. Large class of other varieties are also explicit. We won't go into that, except that one other class of conjectural explicit varieties I will come to in the later part of the talk. But right now, for most of the talk, you can simply assume by explicit variety something like orbit closure of the determinant. That should help for a large part of this talk. Okay. So with that, now because of this result, since for hardness of hypothesis of GCT is expected to hold, there is significant evidence for that. And this variant is also expected to hold. So because of that, we now expect that NNL is in P. Okay. But before we try to show that NNL is in P, we should at least try to show, and we already know that it is in P space. Okay. So the next thing to work on, next intermediate problem to work on, is that NNL is in PH assuming only GRH, generalized Riemann hypothesis. That is obviously the next intermediate step to work on. Now I should say that this is a challenge regardless of whether VPWS bar is equal to VPWS or not. We don't know what is it, but this problem is a challenge. Now if VPWS bar is equal to VPWS, then by the earlier result based on Coherence, Hilbert-Nullstellensatz algorithm, we know that NNL is in PH assuming GRH. Okay, but then the challenge is to show this equality, okay, between these two, and this is related to deep questions in algebraic geometry and representation theory. On the other hand, if these two are not equal, then the task gets even harder, because then you have to show that NNL is in PH despite this inequality. Then you have to really understand the structural complexity of the relative difference between VPWS bar and VPWS. And so because of that, putting NNL in PH is a challenge regardless of whether VPWS bar is equal to VPWS or not. And hence bringing NNL from P space to PH is expected to need overcoming this VPWS versus VPWS bar problem in one way or the other. Okay. But since the VPWS versus VPWS bar problem is related to some fundamental issues in algebraic geometry, as I already mentioned, and representation theory, and I can elaborate that remark a bit more, because in the earlier side I said that VPWS versus VPWS bar problem is related to the structure of the singularities of the orbit closure of the determinant. And these fundamental problems are actually related to the structure of the singularities of the orbit closure of the determinant. And you know that these singularities are bad, they are not normal by Kumar's result. And so this is a huge problem in algebraic geometry, and is basically related to very foundational issues in algebraic geometry, because understanding structure of the singularities of algebraic varieties is the problem of algebraic geometry, and it is actually related to that the problem, which is why this VPWS bar versus VPWS is such a foundational problem. And since this problem is related to all these foundational issues in algebraic geometry and representation theory connected to the structure of the singularities of the varieties, bringing NNL to PH is expected to need a deep synthesis of algebraic geometry, representation theory and complexity theory because of all this. Okay. And so in view of this, I will call the existing P space gap, P space versus P gap, in the complexity of NNL, the GCT chasm, revising the earlier definition of in GCT5 thanks to this work of Forbes and Spilka, Guo, Saxena and Sinhamagu, which I just mentioned, with the understanding that bringing this problem from P-space down to say pH is going to require entry to the battleground of GCT, the VPWS bar versus VPWS. This is what GCT is about. This is the battleground of GCT, and without the battleground, without this GCT is no GCT. Okay, so this is the battleground of GCT, and you would have to overcome deep foundational issues related to algebraic geometry, representation theory. Yes.
Can you explain, for example, if you have a PIT for NNL for VPWS bar in pH, what will it imply? So, like, what I don't understand.
No, this would imply that NNL is in pH.
Yeah, but what it imply about the difference between VP and VP bar?
No, if you can just show NNL is in pH, okay, yeah, as an oracle, some oracle tells you NNL is in pH, okay, then I can't infer anything about VP versus VPWS bar like that, okay. But the other way around, but the two things are intimately related, though I can't prove it formally, okay. And so bringing NNL down from P space to pH, you would need to understand this, but so because of that, so this is what is called, what we will call GCT chasm, with the understanding that now you are entering the GCT chasm, okay, at this point. Yeah.
But this new definition of GCT chasm, isn't it just PIT question?
No, because in PIT question, you know that it is in pH assuming GRH.
No, but you are asking about P space versus P gap, right? So that is the exact gap in PIT also.
Yeah, but that gap can be reduced assuming GRH, okay. So here the understanding is that that gap can be reduced to pH even assuming GRH right now. That is the difference between the two things, okay. Because PIT is in pH assuming GRH, yes. Whereas this is not in pH assuming GRH, and that is what the whole thing is about, okay. To bring, well, that is what I thought the previous thing was, this algorithmic challenge. Show that NNL is in pH assuming GRH, okay. This is what it is related. So, okay, so now, so what I am saying is that this chasm will have to be crossed by any approach to the VP versus VNP problem, which also seeks to separate in the process, okay, VNP from VP bar as per the hardness hypothesis of GCT, and we will call any approach to the VP versus VNP problem which also seeks to separate VNP from VP bar in the process, okay, as a GCT approach in a broad sense. This is regardless of whether that approach uses this notion of so-called multiplicity obstructions or representation theoretic obstructions, which were introduced in the second article in the GCT series, regardless of that, okay. And as I said, any realistic approach to the VP versus VNP problem is expected to be GCT approach in a broad sense, because any realistic approach is expected to separate VNP from VP bar, okay, which is what all the current literature even in our field indicates. So in that sense, this chasm would have to be crossed by any realistic approach to the VP versus VNP approach, regardless of whether it is actually using the notion of multiplicity obstructions. And GCT also provides a systematic program to cross this chasm. Part of it is given in GCT5 and the remaining part will be given in the later papers. Now, I don't have time to go over the whole program on how to cross this chasm and how to bring NNL from P space to P using this. But just to give an idea as to what kind of humongous problems at the interface of algebraic geometry, representation theory and complexity theory would have to be solved to cross this chasm, what I'm going to do is just describe the first step of this GCT program, okay? And that would give an idea as to what kind of difficulties at the interface of algebraic geometry, representation theory and complexity theory would have to be overcome to cross this chasm, okay? And this first step of the GCT program to cross the GCT chasm is the certain orbit closure intersection problem in invariant theory. And now, thanks to Avi, I'm simply going to assume that everybody knows about orbit closures, null cone membership, moment polytopes, and everything. Okay, so that makes my task easier. So And I'm assuming that everybody knows about this now, okay? And so with that, let's begin. So V is a finite dimension representation of a reductive group G, such as SLMC, okay, which is a prime example of a reductive group, but it can also be any finite group, okay? Then the orbit closure intersection problem is given V and G and 2 points V and W in V, decide if the G orbit closures of V and W intersect, okay? This is what the orbit closure intersection problem is. Now the null cone membership problem for V, which Avi talked about in the earlier lecture, is a special case of this problem, which results when W is the origin. Because when W is the origin, this problem amounts to asking if the orbit closure of V contains the origin, which is the same thing as saying if if V is in the null cone. Okay, so the null cone membership problem in the previous talk is a special case of this when W is the origin. Okay, so with that, now let me state a basic result of GCT5 on this orbit closure intersection problem. So for that, I just need a bit of review the terminology which Avi already used. CV is the coordinate ring of V. CVG is its subring of G invariants, as in the earlier lecture, which we know by Hilbert is finitely generated, which Avi also mentioned in the earlier lecture. And then there is a general construction in algebraic geometry, and V mod G be the spec of this CVG, which means that given any finitely generated affine ring with it you can associate a variety whose coordinate ring is that affine ring, and that variety is generally referred to as spec. Here I am taking the spec of CVG is an algebraic variety which I am calling V mod G, whose coordinate ring is CVG, which is the subring of G invariants. Okay. Now this spec actually means it's a scheme, not a variety, but let's forget about that. And this is what is called as a categorical quotient in geometric invariant theory, GIT. Okay. So with that, let me now state the basic result of GCT5. It says that this orbit closure intersection problem is in P, okay, for any finite dimensional representation V of a reductive group G. As Avi stated in the earlier talk, this null cone membership problem, which is a special case of this orbit closure intersection problem, and even orbit closure intersection problem is in NP intersection co-NP by GIT morally, okay. Now this is formally, not morally, and not just in NP intersection co-NP, but in P. It says it is going to be in P formally for any finite dimensional representation V of any reductive group G, if V mod G is explicit. And there is, by explicit I mean its coordinate ring, which is the ring of invariants, has a set of generators which can be encoded by an algebraic circuit small of polynomial time computable. And there is one conjecture in GCT5 which says that this is always explicit, and a bulk of GCT5 actually provides some special cases of these results and provides evidence for why this should always be explicit. But that is the other part of GCT5 which I don't have time to talk about today, so we are simply going to assume that this is expected to be explicit. And white box PIT, which all of us know, is in P. So assuming these two things for which there is non-trivial evidence that white box PIT is in P and that V mod G is explicit, it follows that this orbit closure intersection problem is in P. Okay, and so this result now leads to the general orbit closure intersection.
So just finite dimensional, you mean N is fixed?
Excuse me?
N, when you say finite dimensional, you mean N is fixed?
N mean?
N is like the GL.
The dimension. No. G, not finite dimension. This is M. The dimension of V is fixed.
The dimension of V
no, not fixed. N. Not fixed. N.
So you want things.
What is finite?
Finite is
The complexity, how does the complexity?
Yeah, because when you represent V and G, okay, you are going to give the representation matrices of the generators of G. I didn't go into all that,
Yeah,
okay.
so
that N would be part of the input thing also, because you are going to specify the matrices of the generators of G, okay, and they are going to be N by N dimensional matrices. So N would be taken into account in that.
Yeah,
Okay?
so in the cases, in the examples I gave, they are usually exponential size.
That is fine, but it can be any size. Yeah.
No, okay, it's polynomial in the description of the matrices. Yes.
Yes. And it is also in NP intersection co-NP morally in that sense only, from GIT. So this is formally in the same way that it is for in NP intersection co-NP morally in the GIT sense, okay? But it says it is in P, not just in NP intersection co-NP. So now because of this orbit closure intersection problem is now expected to be in P for any finite dimensional representation V of any reductive group. So that this leads to a basic hypothesis, the orbit closure intersection hypothesis in GCT5, which was stated for the connected reductive groups in the Fox version 2012 and arbitrary reductive groups possibly disconnected in 2017. It says that the orbit closure intersection problem is in P for any finite dimensional representation V of any reductive group G, and in particular the null cone membership problem is also in P, okay? And this is expected to be an inherent difficulty underneath white box PIT because of the result I just stated and some other things in GCT5 which I won't go into, okay? And so what do I mean by inherent difficulty? I don't mean that when you do white box PIT, you have to solve this hypothesis. This is exactly as stated here, okay? For example, there might be an approach to white box PIT which goes through number theory. Then you will have to overcome this difficulty in the setting of number theory, not necessarily the way I have done. So what is the status of this hypothesis? So it is shown, it holds if G is connected and the dimension of G is constant, okay? This is shown in GCT5 for arbitrary reductive group. It holds if V is the space of n tuples of M by M matrices with the adjoint action of G equal to SLMC. Avi described this example in his talk. And in this case, this follows from the Fox version of GCT5 in conjunction with the works of Forbes and Spilka. It also holds if V is the space of is n tuple of space of M by M matrices with the left-right action of G equal to SLMC cross SLMC. Avi described this example in his talk, okay? And in this case, it follows from the works of Gerb, Gurevitz, Oliveira, and Wigderson, which Avi talked, and the works of Duxon and Makam and Ivanios, Kiao, and Subramaniam, which Avi talked about in his talk. 2016 all came around at the same time. Earlier, this work proved this for the null cone membership problem, but now by now this is known to hold for any orbit closure intersection problem also. Now this provides a concrete application of GCT in the sense that this special case of the GCT5 hypothesis above implies a polynomial time algorithm for non-commutative rational identity testing. So you see that all this work on non-commutative rational identity testing you can fits in nicely as a part of the GCT program and constitutes a significant contribution to it. Then the next case is when V is C to the n choose 2 with the natural action of Sn. So n choose 2 corresponds to pairs of integers in the range 1 to n, where each pair you can identify with an edge of an n node graph, and with every edge of the n node graph you assign a weight from C, but actually it would have to be some algebraic number, okay? And then you have the natural action of Sn on this n node graph, which just permutes the nodes of this graph. In that case, the orbit closure, because the Sn is the permutation group, orbit closure is the same thing as orbit because this is a finite group, and the orbit closure intersection problem is the same thing as asking if the two orbits are the same. So this problem is the same thing as weighted graph isomorphism, and this is familiar to all of us. And in this case, it is known by a deep and fundamental result of my colleague Lassi Babai that this problem is in quasi P actually, but I'm going to forget about the quasi prefix X and so assume that Lassi put it in P and whatever, he's not here, so but he put it in P morally, the formality is missing, okay? So now among all the, now I should say that this result is unlike the earlier results, is completely independent of GCT, and GCT played no role in this result, though he is my colleague, and the motivation for this result came from totally different things from GCT. But despite all that, among all the special cases of this hypothesis which have been shown to hold so far, this is by far the deepest and the most significant special case, because the proof of this result depends on classification of finite simple groups, which is a monument of the of the last century mathematics. Okay, so this itself says that now if you want to prove this orbit closure intersection problem is in P for arbitrary finite group, say, which is then the orbit problem of arbitrary finite group, since the classification of finite simple groups was required even when G is Sn, you would expect that classification of finite groups, not just finite simple groups, would be required when G is arbitrary finite group. But that is the most outstanding problem of finite group theory. The problem is the classification of finite groups is not known so far. So every finite group has a Jordan-Holder series, and all the components of that Jordan-Holder series are finite simple groups which have been classified, but we don't know how those components fit, and that is the most outstanding X problem of finite group theory. So this itself indicates that to really prove this hypothesis, orbit closure intersection hypothesis in full generality, one would probably almost certainly need to extend all this technology that goes in the classification of finite simple groups in a deep way to actually prove this hypothesis in a complete generality. And GCT5 says that this is an inherent difficulty in white box PIT. See, even after you prove that in complete generality, you haven't yet shown that white box PIT is in P, you would need to do something more. But at least after you have done it, you have, let us say we have extended all the technology that goes into classification of finite simple groups and shown that this problem is in P, though we would still not have shown that white box PIT is in P, at least we can hope to have made a substantial headway towards showing that white box PIT is in P. But it is humbling that even then we'll be very far from separating VP from VNP, because as I said, this is just the first step of the GCT program to separate VP from VNP. Some additional steps would have to be executed which are far harder. And so let me finally give an overview of the complete GCT program to give an idea of what are the much harder additional steps which would have to be implemented to separate VP from VNP. So the last step, which is what we want to prove in the context of the VP versus VNP problem, is to show that VNP is not contained in VP bar. This is the hardness hypothesis of GCT, and we want to show that using multiplicity obstructions, which were introduced in the second article in the GCT series. And I am saying multiplicity obstructions because a fundamental result due to Burgesser, Eichenmeier and Panova, the recent development shows that the so-called occurrence obstructions do not exist in the context of this problem, contrary to what was conjectured in GCT2. So which basically means there are no shortcut, and now it's going to be a really long haul, and I will say what that long haul is going to be now. Okay, so this is the final. There is a program for actually proving existence of multiplicity obstructions. As a final step of the program, I'm just outlining, but I won't go into that here. Okay, so because there is no chance of showing existence of multiplicity obstructions until we solve this much easier problem, which is basically the problem NNL for general explicit varieties, which is what I talked about in this talk, which by the equivalence result is equivalent to a weaker form of the hardness hypothesis of geometric complexity theory. So first you have to show this, then only you can go about proving existence of multiplicity obstructions. Now there is again a systematic GCT program for showing this and putting NNL for general explicit varieties in P, which amounts to the same thing as crossing the GCT chasm. Again, I don't have time to go into that program today, so I'm just going to describe the first two steps, initial steps of that program in the next thing. And the next step, which is much easier, and which is, so part of this program is given in GCT5, the remaining part will be given in the later papers. So the first two steps, out of that the second step mentioned in GCT5 but not covered in this talk, is to show that the problem NNL for the categorical quotient V mod G, which the conjecture in GCT5 says that is explicit, okay, that is in P for any finite dimensional representation V of any reductive group G. Now assuming that categorical quotient is explicit, this is a formal implication of the general problem NNL for general explicit varieties. And it is also much easier. The reason for that is that as I said, the singularities of the orbit closure of the determinant are not even normal. That is Shravan Kumar's result. whereas the singularities of this categorical quotient V mod G are not just normal, but they are also so-called rational, and they are Cohen-Macaulay and so forth. They are as nice as you would want them to be, not we, the mathematician, would want them to be. Whereas the singularities of NNL in general, explicit varieties in general, are nasty. So there is a huge jump in the difficulty when you go from here to here. Okay, so this is, in that sense, in a formal sense, much easier than this problem that you want to solve. Okay, so this is what you want to solve next, but even this is much harder. So then we go to the easiest problem in GCT5, which was covered in this talk, which is precisely show that the orbit closure intersection problem is in P for any finite dimensional representation V of any reductive group G. Okay, this is the easiest first step. By no means it is easy, because as I said on earlier thing, that to prove it in full generality, you would have to extend this whole massive machinery of classification of finite simple groups, and which is a huge task. So this is a real serious algorithmic challenge, not easy by any stretch of imagination. And the program is first prove this by doing whatever is necessary, then extend that proof to prove this, doing whatever is necessary, then from here go to here, and then there is a systematic program, because there is a huge jump in the difficulty of singularity. Then there is a program for how to overcome all the problems in algebraic geometry and representation theory related to the structure of singularities, which need to be overcome to go from here to here. And then there is another program to overcome additional problems that would need to be overcome to finally show existence of multiplicity abstractions. Once that is done, VNP is not contained in VP bar, and VP is not equal to VNP. Okay.
So suppose tomorrow I come with an example of the easiest problem, even an easier problem, the null count problem, an explicit variety for which this problem is NP hard. What would it do to your program?
Well, as you already said, that it is morally in NP intersection co-NP, so it would mean
but
that...
morally, but it's not formally. And
No, but for finite groups, for example, it is actually...
No, not finite, SLM. So, or TM for the torus action. Suppose I come in tomorrow with a torus action for which the null count problem, easier than orbit intersection, is NP hard. It's possible.
No,
for an explicit variety that I give you. Suppose I had one.
Yeah.
What will it do to the program?
Well, then you will have to come up with something to adjust it. Yeah. But what I said is that morally, GIT says that it is in NP intersection co-NP. Okay. So, and of course, I knew about the morality of GIT before I came here. So, yeah.
So by morality, usually we're talking about, like, these are exponentially large.
No, but I will tell you, morally, GIT also tells you that when connected case is always much easier than the disconnected case, the finite group case. And for the finite group case, we know not just morally but formally, because all these graph isomorphism algorithms, okay, earlier graph isomorphism result that it is in NP intersection co-AM, okay, that actually generalizes formally to even the finite group case. So it is in NP intersection co-AM, not morally but formally, and GIT tells you that this is much harder than the connected case. So this is not going to happen.
However, there are connected examples like actions of torus actions on tensors, which we don't know formally that it's in NP intersection NP. They might be NPR.
No, I mean, but
just pointing this out.
No, of course. But all I'm saying is that the representation theory, for example, you know that the tensor products of, for example, if you take the irreducible representations of the two SN representation, then understanding the structure of this is the Kronecker coefficient problem, which is much harder than when it is connected. Okay, so there is a lot of literature in GIT which says that the disconnected case is always much harder than the connected case. So assuming that all this last century thing, the lessons that GIT has taught us don't go wrong, and I don't think they will, we are fine. But if otherwise, then it means that GIT was something, but it may get even more interesting than this, and then the GCT would get even harder than what it is. Well, but then we'll deal with it. Okay. So now, just 5 minutes. Yeah, in 5 minutes. So now you see that this is what the overall program is, but you can see that I have to say that these difficulties are not specific to GCT. Okay, these are the inherent difficulties, because as I have said, that assuming that any realistic approach to VP versus VNP would separate VNP from VP bar, assuming that this problem NNL would be in P, assuming the variant of that. So there is a formal equivalence result. So this is going to be done. So that GCT chasm is a difficulty that would have to be crossed by any approach, any realistic approach to VP versus VNP, regardless of whether you use multiplicity obstructions or not. Okay, so this is an inherent difficulty in the any realistic approach to VP versus VNP. Then this is a formal implication of this, assuming that these varieties are explicit for which there is a significant amount of evidence. And then this also is a formal implication. I didn't go into it. That is the other part of GCT5. So there is a formal equivalence there and the formal chain of implications, because of which we say that these are the inherent difficulties in the VP versus VNP, regardless of whether you use multiplicity obstructions or not. So it is not that GCT program is hard because we just want to do something hard, but it is hard because the VP versus VNP problem is hard. And in a sense, these inherent difficulties of the GCT program would have to be hit one way or the other. Okay, so in that sense, morally or realistically, there is no really realistic alternative to GCT at the point that one way or the other it is going to be GCT. You will have to hit these inherent difficulties. I don't mean to say exactly the way it has been done. For example, if you were to go through number theory, a theory of automorphic forms, this would be encountered in number theory. But you see that this is such a massive challenge, like classifying finite groups, and so just because you reformulated that in number theory, the deep extensions of classification of finite simple groups which would be required here, those difficulties are not going to just disappear just because you reformulate this. So what I'm saying is that there could be several different forms of GCT. This is one form of GCT. There could be several others up to equivalences and reformulations and so forth. But one way or the other, it's going to be GCT. And so the theory of computing has to simply get used to this idea that now it is going to be GCT in one way or the other, and that which is why this program is so important for the future of theory of computing, because it seems now that there would be no realistic alternative to it, and we have to overcome all these intrinsic difficulties. But given the scale of difficulties, this is really going to require a deep collaboration among all these fields: theory of computing, complexity theory, algebraic geometry, representation theory, group theory, so forth. A significant amount of collaboration has already occurred, without which we won't be even here today. Because, for example, there was a special semester on GCT with focus on GCT in Simons Institute a few years ago, and so there was a lot of collaboration already happened. But given the scale of difficulties, this collaboration has to be at a much deeper level. Okay, and it is my hope that all these fields, algebraic geometry, theory of computing, representation theory, group theory, invariant theory, will come together and collaborate at the deep level as required to take this program much ahead from where we are today. And with that hope, let me stop here. Thank you very much.
Questions? Maybe a comment. So I think looking at this table, I really think that if we go to the easiest problem, orbit closure intersection problem is in P, I think it would be very good to, like Avi had, he said that the Malcolm membership problem is in NP and Conti morally, so we don't have the formal proof. It's probably true. But here, for the orbit closure intersection problem, can we see any evidence that it is in Co and P? So can we have a witness?
The way I came, the way I came about it, okay,
yeah, so
the way I came.
more confidence that say the easiest step of this program actually.
Yeah. So the way I came to it is that all the literature in GIT suggests that when the group is finite, it is always much harder than the connected case, like Littlewood-Richardson coefficient versus Kronecker coefficient and so forth. And for finite things, we know it formally that it is in NP intersection coem by this graph isomorphism. Okay, so that was my motivation. Okay, so and there is a substantial amount of evidence in GIT which says that the disconnected case is much harder than the connected case. So assuming that, assuming that the morality of GIT doesn't go wrong, okay, we should be fine. But to prove everything formally, I mean, that's why I said we need a deep collaboration among all these fields so that, you know, everything is now formalized and streamlined and so forth and so forth.
So I see a question from Russell. I have a question.
So,
Yeah, question. Who has question?
what's known about the closure of VNP?
Right.
What is what?
Known
VNP
about
closure.
What is?
Is VNP equal to VNP closure? Is that an open question?
VNP?
Equal to its own closure.
Oh, yeah. VNP is equal to VNP closure. That is also an open problem, okay? And yeah, as I said, that is a basic discovery of GCT, that this closure operations, we have to understand it, and, you know, that is very important in the context of VP versus VNP. So even that is an open problem, yes. VNP closure and VNP, right? Yeah, that is we know these closure operations only in special cases. Like, for example, if you take read once oblivious algebraic branching programs, its closure is equal to ROABP, okay? So in some special cases we know, in restricted algebraic models, okay, like ROABP, everybody is familiar here. In that case, the result of Nissan, in which the non-commutative model was proposed, some result he proved actually says, though he didn't put it in this language, that ROABP is equal to ROABP bar. He didn't put it in that language, but except for these very, very special cases, you know, this closure operation is, and that was actually the basic discovery of GCT, that this is such a havoc, and, you know, it is standing in the way, and it is not at all, because earlier, before GCT, it thought this is just some minor extension. It's not minor, it's a huge problem, and it's standing in the way, yeah.
Michael?
So for this easiest problem,
Sorry, can you just go back one slide, get them scrolled forward? Yeah, good.
So the invariance for this action, I mean, do we have these sub-exponential degree bounds in this case?
Excuse me?
With the invariance on this action, but like for a general setting here, do we?
Yeah, there is a Dirksen.
Exponential. You cannot improve it in general.
You can't improve exponential, but there exponential. Dirksen's result works in full generality. Yeah. You had.
No, it was the same question that Russell asked. So. Right. So thanks very much.
Okay.